Then I can write lambda 1 as lambda 2, or I can write lambda 2 is equal to lambda 1, right? Remember, we are trying to get a matrix such that we can represent lambda 2 x2 as a multiplication or a product of this matrix for translation times lambda 1 x1. So we have these two relationships. I'm going to write the same thing here. Lambda 2 is equal to lambda 1 and x2 is equal to x1 plus d times alpha 1, right? Um, so technically, here we are also supposed to put in the refractive index, but in the sense that um, we define lambda 1 as alpha. Sorry about that. So we got these two equations. What I was trying to say is we define lambda 1 as n alpha 1, right? So I can write alpha 1 as lambda 1 by n. Because remember what I said, that we defined this direction cosine, right? And we want to represent everything in terms of lambdas and x's. And so we want to remove any other terms like this alpha 1 here. So to do that, we go back to the definition of lambda 1 and rewrite alpha 1 as lambda 1 over n. So that is equal to x1 plus d times lambda 1 by n, right? So then now I can write lambda 2 x2 is equal to lambda 1 or x1 plus d by n lambda 1. So now in this set of equations, everything is in terms of constants or lambda and x. D and n are constants, lambda and x are the only variables. So now it's very easy to represent this in the matrix form. On one side I have lambda 2 x2, on another side I want lambda 1 x1. So I want to make lambda 2 equal to lambda 1. So I must have a 1 here. And I don't want any terms related to x in this equation. So I must put a 0 there, right? And in case of x2, I need to put x1 plus something because I need to have 1 x1. I'm going to put a 1 here. And the coefficient for lambda 1 is d over n. I would have d over n. So what does this do? This gives us the matrix for translation. So matrix for translation then would be simply 1 0 d by n 1, where d is the distance between x2 and x1, 2 points. So if you have the initial point lambda 1 x1 and you want to figure out which way light is going to go at another point x2, then you know the distance between x1 and x2. So you have all the elements that are needed for translation, and you can just plug in this matrix here and then figure out what would be lambda x2. This is sort of straightforward in case of translation, because if you're in a homogeneous medium and you're translating, the angle is not changing. You're literally just going an extra distance. That's about it, right? So it looks easy, but it becomes very useful later. So this is how we derive the matrix for translation. Now let's do the same thing for refraction. So to do refraction, now let's consider a spherical surface here. So I have a spherical surface, and let's draw the optical axis here. So let's say we start from point A, right, which is going to be incident on the lens somewhere there, and this point where it is incident we are going to call it P, right? And then this would be the normal. The normal would be going through the center of the curvature of the spherical surface. So the center of curvature is somewhere here, so the normal would just go through the center of curvature. So this is the normal axis, this is the center of curvature. So then this angle is the angle that's going to be uh, theta 1, that is the angle of incidence with respect to the normal, right? And then let's say the ray is going to get refracted. Let's say the ray is going to get refracted, okay, and let's call that angle, the refracted angle, as theta 2, okay, and it is going to get refracted to a point, let's call a prime here. So the incident angle is theta 1, the refracted angle is theta 2, and the refractive index on this side is n1, and inside the spherical surface is n2, and we're going to denote this height from the axis, optical axis, to the point P where the ray of light is incident on the spherical surface as x, right? And the radius of curvature is of course r, right? So now we know from Snell's law that n1 sine theta 1 should be equal to n2 sine theta 2. That is the simple law of refraction. So we also started with the paraxial approximation, meaning that for small angles, for paraxial rays, sine theta is almost equal to theta. So then I can write as n1 theta 1 is almost equal to n2 theta 2, right? So now what we will do is we'll draw a horizontal here through the point P, the point at which the rays are incident. So through this point we'll draw a horizontal there, right? And we call this angle with respect to the horizontal as alpha. If you recall our discussion on translation, we call this angle with respect to the horizontal as alpha. So this would be, we can call this as alpha 1. Call this as alpha 1, the angle with respect to the horizontal, right? And the angle with respect to between this and the normal, let's call that as phi 1 here. The angle between this and the normal, this one, we call it phi 2. So get the angles right. The angle between the incident ray and the normal, that is here, is theta 1. The angle between the incident ray and the horizontal passing through P is alpha 1. Phi 1 is the difference between theta 1 and alpha 1. Same thing with theta 2, that is the total refracted angle between the ray that is refracted and the normal. Alpha 2 is the angle between the ray and the horizontal passing through point P, and phi 2 is the difference between theta 2 and phi 2. So now I can write this mathematically. I could write theta 1 as phi 1 plus alpha 1 and theta 2 as phi 2 plus alpha 2, right? So now because this angle is phi 1, the angle between the normal and the horizontal, so this is the normal, this is the horizontal, so this angle should also be phi 1. So now if this angle is phi 1, then I can make an approximation that tan phi 1 would be opposite side, which is this, right? And ignoring this tiny little distance here, ignoring this distance, I can write tan phi 1 as x over the adjacent side r. One thing you have to be very mindful of is when we are doing geometrical optics, even including the matrix methods, we are making a lot of approximations. We have made approximations of paraxial rays, and we are ignoring tiny distances, like for example this one. These are all approximations. So that's why geometrical optics is also called first order optics. It's not an exact uh, ray tracing technique. We are making several assumptions, and you have to make sure before you apply these equations, you have to make sure whether your system is well within the limits of the approximations that you made. So be mindful of the approximations. So tan phi 1 is equal to x by r. For small angles, I can write phi 1 as x by r, right? So we know that n1 theta 1 is equal to n2 theta 2, and we know this about theta 1 and theta 2. So then I can write n1 theta 1 as n1 phi 1 plus alpha 1 is equal to n2 phi 2 plus alpha 2, right? So then I can write this as n1 phi 1 plus n1 alpha 1 is equal to n2 phi 2 plus n2 alpha 2, right? Or I can further write this as n2 alpha 2 would be equal to n1 alpha 1 plus n1 phi 1 minus n2 phi 2, right? So then if I want to if I want to write instead of phi 1 and phi 2, then I can write this as n1 alpha 1. Phi 1 is x by r, right? Phi 1 is x by r, right? Similarly, if you look at phi 2 is the angle between the horizontal and the, so here phi 1 is the angle between the normal and the horizontal, right? And so we can make another approximation here, that if I look at if I look at phi 2, that should also be the same. So if I look at phi 2, that is also the angle between the horizontal and the normal. So even for phi 2, the same relationship of x by r holds. So I can write phi 1 and phi 2, because phi 1 and phi 2, here phi 1 is the angle between the normal, right, that is going through the center of the curvature, and the horizontal, that's phi 1. So this angle is also same thing. So between the horizontal and the normal, so that would be the same as phi 1. So that's why we are able to write it as x by r. So I would have minus n2 x by r here, or I can write it as n1 alpha 1 plus n1 minus n2 divided by r times x, right? So I have written n2 alpha 2 as n1 alpha 1 plus n1 minus n2 by r times x. So now I'm going to take this equation out because we define lambda 1 as n1 alpha 1 and lambda 2 as n2 alpha 2, right? And the equation that we got was this in the last slide. So we're going to rehash this in lambdas. This is lambda 2 and this is lambda 1 plus whatever this term is. So that's what I'm going to write on the next slide. So lambda 2 is equal to lambda 1 plus n1 minus n2 by r times x, right? So for the sake of convention, we're going to define this power as p as n2 minus n1, not n1 minus n2, n2 minus n1 by r. So then I can write lambda 2 as lambda 1 minus p times x, right? And so this is called the power of the refracting surface. We have seen that, like how it is inversely inverse of the focal length before, right? So now we have a relationship that is lambda 2 is equal to lambda 1 minus px, right? So so now then we can use this equation to write the matrix matrix form. right? And here what we are going to do is we are going to only look at the act of refraction, right? So the height of the ray uh, before and after refraction is going to be the same, right? That is, we are going to consider that the height of the ray is uh, so let's go back to the previous one here. So if you look at this if you look at this part, right, just before and just after refraction, so I'm not considering the height at point A and at point A prime. I'm considering the height within the very near vicinity of P. So just before the light hits the refracting surface and just after the light comes out of refracting surface, it is almost at the same height. It just enters P right here and comes out right next to that, right? So at this point or at this point, if you compare the height with respect to the optical axis from here, it's almost equal to the height of point P. So that's why we are going to equate x2 is equal to x1 here. And then if you look at lambda 2 x2, then I can write it in terms of lambda 1 x1. I can write it as 1 because lambda 2 is lambda 1 minus p times x1, and then I have this should be 0 and 1, right? So this would be our matrix for refraction. This is our matrix for refraction. So one thing to note here again, I made this x2 is equal to x1 because when we are looking at the spherical surface, I'm only considering, suppose a ray enters here and gets refracted there. At this point, I'm only considering at this point P, this is at a height of x1, let's say, right? I am considering the ray of light just before point P and just after point P. So the height just before and just after is the same. So that's why I'm calling it x2 by x1. I am not worried about how the ray is going to get from an object that is situated here all the way up here. Because what I'm going to do is, if I want to figure out how the ray is getting translated from O all towards P just before it refracts, I'm going to use the translation matrix that we developed. Right at P, when the ray is incident on the spherical surface, I would use the matrix for refraction. And then right after it is refracted, I can use again another translation matrix to see where the light goes, right? So now if I use both translation and refraction matrices together, I can trace the ray through the system. So first we have translation in medium 1, then we have refraction at the surface, and then we have translation again in the other medium, right? So I can start with this matrix, then this, and then the final translation to get where the ray of light is going, right? So, so that is the refraction matrix. So you can actually look at uh, imaging by a lens right now, because we know how we can use our matrices. Just before we go there, let's recall what we wrote as the translation matrix. The translation matrix was 1, 0, the distance between the points x1, x2, divided by the refractive index of the medium, and 1. This is the translation matrix. And the refraction matrix is 1, right? And 1, and we have we did we have so we have minus p 0, 1. So these are the matrices for translation and refraction. So we're going to use that to look at, say now I have a spherical surface, right? And now I am starting from here, and the coordinates here I define as lambda 1 x1. I want to know, so this is my object, I want to know where the image forms at some lambda 2 x2, right? And you know that this distance between the object and the lens or the refracting surface is the object distance, which we will indicate as u, and the distance between the image and uh, the refracting surface is the image distance, which we will denote by v. Okay, so now first thing I need to do is, any ray of light that's going from the object O, it has to translate all the way to the surface. So first I need to use a translation matrix, right? So if I translate lambda1 x1 all the way to just before the refraction, which I will call as lambda prime x prime, then I can write lambda prime x prime just before the refraction. So this is just before. So we getting this through translation. So I'm going to use the translation matrix 1 0, right? And then I have to use d by n 1 times lambda 1 x1, right? So now this distance d is actually the distance between this point and this point, the horizontal distance. So that would be u. So when I say distance, it is not this distance along the straight line, it is the horizontal distance. You project them onto the axis, and what is the horizontal distance between them. So that is u, right? But remember our sign convention that anything that is onto the left side of the lens, we consider it as negative, right? And anything that is onto the right is positive. So this distance u is being measured from this point towards the left, so we make it negative. So the first translation in this case, going from O to say point P here, then we would have lambda prime x prime is equal to 1 0 minus u by n1. So this the refractive index of the system here, times 1 lambda 1 x1. Now once you have reached lambda prime x prime, that is point P, you are going to refract because that's right on the lens. So then after the first translation, we need to use second refraction. But the point that's going to get refracted is lambda prime x prime. So lambda 1 x1 got translated to lambda prime x prime, and then lambda prime x prime is the one that's going to get refracted. So let's say it's going to get refracted to right after the lens. Let's call it lambda double prime x double prime. So then I can write lambda double prime x double prime in terms of lambda prime x prime, and I use the refraction matrix 1 minus p 0 1, right? So now we have gotten this thing that we are right here, right after the lens, right? And then I want to figure out how it goes to the image, right? So I take lambda double prime x double prime and translate it to lambda to x2. So then the third matrix I'm going to use is lambda to x2 is equal to translation of lambda prime x prime, but it's in a different media of refractive index n2. So I would have 1 0 positive v by n2 and 1. Here we have positive v because v is on the right side, image is on the right side, right? So we started with lambda 1 x1. Lambda 1 x1 gets converted into lambda prime x prime. Lambda prime x prime goes into lambda double prime x double prime. That's the refraction. Then you translate lambda prime double prime x double prime to lambda 2 x2. That is the image. So then I can combine all these three matrices and write lambda to x2, that is the image, would be equal to 1 0 v by n2 1, that is the last translation, then the refraction before that, then the first translation times lambda 1 x1, right? So this is a simple matrix multiplication, right? And if you perform that matrix multiplication, then you can see that lambda 2 x2 is equal to 1 plus p times u1 by n1 or u by n1 minus p. Then here you would have v by n2 1 plus pu by n1 minus u by n1 1 minus Vp by n2, right, times lambda 1 x1, right? So if I'm given lambda 1 x1 and the power of the lens, right, I can figure out where lambda 2 x2 is. Or from this I can write x2, right, as I can write x2 as v by n2 1 plus pu by n1 minus v by minus this is minus u by n1 times this is multiplied by lambda 1 plus 1 minus vp by n2 multiplied by x1, right? So now we'll consider a special case of x being equal to 0. What if x1 is equal to 0? So what does that physically mean? Always remember that we are doing these mathematics, but never forget the physics behind it, right? So x1 is not just a variable, it has a meaning. That is we considered when we were deriving that x is the height, right? For example, that is the height. At this point, x would be this much. At this point, x is this much, right? So if I consider x to be 0, that means my point is right on the optical axis. And if the point is right on the optical axis, it's going to go through the lens here, because if it is right on the axis, it is going to meet here at an angle of 0. So then it is also going to get refracted at an angle of 0. So it's just going to go through the line. So if x1 is 0, that is you are starting from a point on the optical axis. Suppose you are starting from here on the optical axis. It makes 0 angle at the refraction surface. So it comes out on the other side also at 0 angle. So x2 should also be 0. So if x1 is 0, then x2 should also be 0, because for the reason that I just mentioned, that you will be incident along the normal. So theta 1 will be 0, so theta 2 should also be 0, right? And so therefore you would basically get the ray of light that is going through the optical axis passes straight through without changing height, right? So if I set x1 is equal to 0, then this part is 0 anyway, because x1 is 0. So by our logic, what we have seen from a physical standpoint, if I set x1 is equal to 0, that is, if the object is on the optical axis, then the corresponding refracted ray should also be on the optical axis, because the net refraction angle is 0. So then somehow this coefficient for lambda 1 must go to 0 for it to obey. If x1 is equal to 0, x2 is equal to 0. So then we have to set this equal to 0 to get the right matrix. So then if I do that, I'm going to set v by n2 times 1 plus pu by n1 minus u by n1 is equal to 0, right? Then I can write that as v by n2, right? 1 plus pu by n1 is equal to u by n1, or that is v by n2 plus v by n2 plus v times p times u by n1 n2, right, is equal to u by n1, right? Or I can write this as v by n2 minus u by n1 is equal to minus v u p by n1 times n2, right? And if you look at this a little more, right? If you take the inverse of this, right, then you can get so I can write this as, for example, I can write it as n1v minus n2 u divided by n1 n2 is equal to minus vu minus vup by n1 n2. So n1 n2 cancel out. Then I can write this as n1 v minus n2 u is equal to negative vup. So if I divide all throughout by vu, then I would get n1 v divided by negative vu. Then this will be positive, so it will be n2 u divided by vu is equal to p. So here v and v cancel out. Here u and u cancel out. So I would have n2 by v positive minus n1 by u negative is equal to p, which is the same as the thin lens equation, if you recall, of what we derived doing the doing it with the arrays, right? So now we have derived this successfully just using the matrix method. But now let's go back to the matrix that we had. So the three product matrices. This is for translation from object to the lens. This is refraction, and then again the translation to the image, right? And the overall matrix we got was this, and we had set this term, this entire term, to 0, because if x1 is 0, x2 should be 0. So we had set this entire term to 0 to get the thin lens equation. So now I can write, after setting this to 0, because we arrived at the conclusion that this entire term should be 0 because this law is obeyed, right? Because this law is obeyed, this entire term is 0, right? We just derived it the other way around. So now if I truly write the matrix, then I would have lambda 2 x2 is equal to 1 plus pu by n1 minus p 0. This is the term that we showed it to be 0 minus vp by n2 lambda 1 x1. So the only thing that I changed from the previous matrix up here is I set this third term to 0, as we have seen from the physical picture, right? So then I have lambda 2 x2 in terms of lambda 1 x1, right? So now I can write x2 then as the first term is 0, so no lambda 1 appears. I have 1 minus vp by n2 times x1, right? So now x is the height of the object, right? So if I had a lens here, if I have this object here, say ray of light is going from here, this height is x1, right? And the image say forms somewhere here, right? And this height is say x2. Then we defined, remember we defined magnification as height of the image by height of the object, so that would be x2 by x1. And from this equation, it is simply 1 minus Vp by N2, right? And if you were to use this other equation, N2 minus N2 by V minus N1 by U is equal to P, to derive the magnification, then you would get magnification as N1V by N2U, or it is 1 minus Vp by N2. So in this lecture, basically what we have looked at is we have established matrices for translation and refraction. I will also upload a PDF file. I would urge you to go through those and do these things yourself so you understand where we are coming from. And then after having established the matrices, we have seen how we can follow the path of a ray just by using matrices. For example, we did translation, then refraction, followed by translation, to look at how a ray from an object goes through the refracting surface and goes to the image, right? And from this matrix, we were successfully able to reproduce the thin lens equation, which was n2 by v minus n1 by u is equal to n2 minus n1 by r, or it is just simply p, the power, right? And By writing the matrices, we also came up with an equation for the magnification, which was the same as the one that we derived earlier. Just that using the matrices, it becomes a little easier, right? So I will stop here, right? And then we will work on some more matrices in the next lecture, and then do some problems so that you can see the power of this matrix method and how to use it so easily without having to worry about actually tracing the rays. Thank you.